Welcome back to Advent of Code 2025. So today we have a factory with a bunch of machines, and each machine is specified in a line. The manual describes three components to a machine. The first line is an indicator light diagram with a bunch of indicator lights represented as dots for off and pound signs for on. A number of buttons, which are written in space separated round brackets with comma separated integers denoting which indicator lights the buttons affect, or which machines the buttons affect. And finally, the joltage requirements for each of the components in curly brackets. And so for part one, we're ignoring the joltages. We must first start up the machines. So the indicator lights have to match what's shown in the diagram. So initially, all of the indicator lights are off, and each time we press a button, we toggle all of the indicator lights that are represented here. So for example, in this set, if we hit the fourth button with the set 2, 3, then it would turn on lights 2 and 3. And so the joltage requirements are ignored because none of the machines are running yet. We can push each button as many times as I want, but we want to find the fewest total number of presses required to configure all of the indicator lights. Okay. So I did not find a solution that was particularly better than just brute forcing. We simply start by trying every single button, and then every pair of buttons, and then every 3 buttons, and so on and so forth, until we find some number of buttons we can press to match the indicator lights, and then we just add the number of buttons we had to push to the total. So first, grabbing our input. This input is not the most friendly to parse. We'll use regex, so import re, and then keeping track of our total for each line in our input, we'll expect the regular expression to match something like this. So we'll have square brackets first with a bunch of dots and pound signs. And then we'll expect a bunch of space separated round brackets. So this will consist of open and close brackets, digits, commas, and spaces. And then finally, we'll expect curly brackets with a bunch of comma separated digits like so. And so let's print out the match groups to see if I've actually done this correctly. These are our groups. So we'll get this match, we'll grab the groups, and then the 3 parts to it will be the lights, or the indicators. I guess we'll call it target for the target indicator light configuration. The buttons and the joltage requirements can be ignored. And so that will equal matched up groups. So now if we print out the target and the buttons, that's what we get. To make things easier for ourselves, let's parse the target into an array of true and false values. So target like so. And the buttons we will want to parse into sets. So actually, correction. The way I'm going to do this is using set XOR, which basically allows us to toggle everything in the button set we press. So we're actually going to store the target as a set of indicator lights that should be on. So it'll be index for index light in enumerate target if light is equal to pound sign. Yeah, so basically we want to reach this set. So for the first example, we need lights 1 and 2 to be on. For the second example, we need only light 3 to be on, and etc. And the buttons will be like so. And then for each one, we will slice the brackets off, split it on commas, and then parse those all to integers. So that's what we'll have, and we'll want that as a set. So I mentioned the set XOR operator. So in Python, we have an operator for symmetric difference, which is the caret, which is the same as bitwise XOR, if you're familiar with that. When you take the symmetric difference between two sets, you are returning all elements that are in exactly one of the two sets. So if we take the symmetric difference of two sets like so, um, it's A minus B union with B minus A. So we're basically subtracting each element of each set from each other. So the twos would cancel out here, and so that's how we'll implement toggling. So if our set is currently 1, 2, and we press a button that toggles lights 2 and 3, the symmetric difference will allow us to toggle all of these values, because if it's already in the set, it will get removed, and if it's not in the set, it will get added. So we'll also import itertools, I guess, which will help us. Itertools is basically a utility module for iterating through stuff. And so let's implement the approach I described earlier. So for each count, which is the number of buttons we'll attempt in range from 1 up to the number of buttons inclusively, basically we'll start at 1 button, and then if we can't find any set of 1 button alone to match the target, we'll try all sets of 2 buttons, and then all sets of 3 buttons, etc. That's the function itertools dot combinations, which we can pass an iterable and an r value, which will give us the length. So you can see in the documentation example, if we gave it all 3 length combinations of range 4, then we get 0, 1, 2, 0, 1, 3, 0, 2, 3, and 1, 2, 3. So that gives us all of the possible sets of buttons we could try. So for attempt in itertools.combinations, we will see if this matches the target. So initially, all of the lights start out off. So lights equals empty set. And then for each button, we'll use the XOR operator to toggle all of those buttons. And then if the lights that end up on after we've pressed all of those buttons is equal to the target, then we know that count works, so we can add count to the total. Or yeah. So what this is basically doing is we'll gradually increase the number of buttons we try each time, and each time for each set of buttons of that length. If that matches the target, then we'll add that to the total. And once we found our target, we will break. And then we also need to break out of this for loop as well. 2 ways of doing this. The first is you can set a found flag like so. Like that. That is not the way I prefer to do it. The way I prefer to do it is like so. I have a YouTube short explaining this in more detail, but essentially what's going on is when you break out of a for loop, it goes to the end of the for loop. So it skips to the end of this entire block and goes to here. If you don't break out of a for loop, then it'll go to the else block that's attached to the for loop. And so what this is basically saying is if we find a match, then we break, we skip over this, and then we go to line 20 and break out of the outer for loop as well. So that propagates the break back up. If we don't break and we didn't find anything that works here, we'll go to the else block and continue to the next count and skip over line 20. Basically, else continue break just allows you to propagate breaks from the current for loop to the next loop upwards. And okay, let's see what's going wrong here. Oh, yes. Typo I made here. I should be trying all of the buttons in the attempt set, not trying to press all of the buttons each time. Okay. That gives us 7, which appears to be the correct answer for the example. And running this on the actual input, we get our answer for part 1. Moving on to part 2. We now have the machines online, and now we need to worry about the joltage requirements. So we are now ignoring the indicator lights as those were already set correctly. We need each machine to be configured to exactly the specified joltage levels. So it must be exactly equal, cannot be higher. And we can flip a lever to switch the buttons from configuring the indicator lights to configuring the joltage levels. So we now ignore the indicator light diagrams totally. The machines each have a set of numeric counters tracking the joltage levels, 1 per joltage requirement, and initially they're all set to 0. So for example, the first machine's joltage requirement of 3, 5, 4, 7 means that it has 4 counters that are all initially 0, and we have to set them to 3, 5, 4, and 7 in that order. In this new configuration mode, each button now indicates which counter it affects, so pushing a button will increase the joltage of each item in its set. So basically, it's exactly the same as the first problem, but without the but instead of toggling, it increases. So it's like modulo 2 basically. So now we need to determine the fewest total presses to correctly configure the joltage levels. Okay, so let's first describe this problem in theory, and then today, unfortunately, I will be solving it with a library. You can, of course, theoretically solve this without a library. It just is that I wasn't really able to find a relatively straightforward way to do so. It requires some non-trivial optimization knowledge that I unfortunately don't quite remember. So essentially, what we can observe is that the number of times the joltage that we end up with in slot 3 is equal to the sum of the number of times we press the first, second, and fourth buttons, because the other buttons don't affect the third joltage, and each of these 3 buttons increases the joltage by 1. That means that essentially what we have is if nx equals the number of times we press button n, then it follows that n1 plus n2 plus n4 must equal the joltage for 3, which is 7. So basically what that's saying is the total number of times we press the first plus the second plus the fourth buttons has to sum to 7. Likewise, only buttons 5 and 6 affect slot 0, so that's saying that n5 plus n6 has to equal the joltage of slot 0, which is equal to 3. So this eventually gives us a system of linear equations. And we need to find the solution for this that minimizes the total number of presses, which is just the sum of all of the n's. And so formalizing this problem, we are trying to find the minimum for a vector n, which is in z to the power of the number of buttons. So all of these have to be integers because we cannot press a button a fractional number of times. So we're trying to minimize over all possible vectors of size b, where b is the number of buttons we have, the sum of n, so that's the dot product of n with the one vector, subject to the constraint that n is greater than or equal to the 0 vector, because we can't press a button a negative number of times either, subject to the constraint of the linear equations we have here. So those can be represented as a matrix and a vector. Basically what this is saying is that the configuration of the buttons dot product with the vector of the number of times we press the button has to equal the joltages. So let me briefly take an aside to explain this. We can represent this as a matrix because what we've basically done is this. So in case you're not familiar with matrix vector multiplication, when you multiply a matrix by a matrix, the result is a matrix where the value at each position is equal to the dot product of that same row from the first matrix and that same column from the second matrix. And the dot product of two vectors is the sum of the element-wise product. So if you take the dot product of A and B, it's equal to the first element of each multiplied together plus the second element of each multiplied together, etc. And so that's what dot product does. That's what matrix multiplication does. And so, for example, our constraint here would be something along the lines of this. And so this tells us that the last row multiplied by the first column, which is also the only column, must equal the last row and first column of this. And so this constraint says basically 110100 dot product with n1 through n6, which is equivalent to n1 plus n2 plus n4, must equal 7. And so that's how this system of linear equations can be represented as a matrix vector multiplication. And so this ends up being our problem. So this is known as an integer programming or integer linear programming problem because we have all linear constraints and we have a linear optimization target, and we also have the constraint that one or more variables must be integers. Now, there are many ways to solve this, but I'm not going to explain them. You can look through the Wikipedia article for linear programming. I learned about this in a second-year university course, so this does seem a bit high level for trying to approach without libraries for an Advent of Code problem. I'm not sure if I'm missing something and if this is just a special case that somehow you can solve without using integer programming in like itself, but I'm pretty sure it's not a special case because the way I've described the problem is quite literally the template for all integer programming problems. And if this could be easily solved, then we would have a lot of issues. I was discussing this with a friend, and since IP is NP hard, being able to solve this easily would kind of break a lot of things. So we're going to use Z3, which is a library that allows us to solve stuff. So I'll go over Z3 as we implement this. I didn't really find great documentation on it, to be completely honest. It took me a while to figure it out. This does not come with a standard distribution of Python, so you'll have to install it separately. Do be sure to install Z3 Solver, because if you install Z3 itself, then nothing will work. You're just supposed to know that, I guess. So we'll import RE and Z3. And we'll ignore the Pylance warning because I can't be bothered to set it up correctly. So we no longer need the indicator lights, and we now do need the joltages. And we now want to parse the joltages as an integer list. So we'll do joltages equals list map int joltages split comma. And now let's specify our problem. So we'll begin by creating a Z3 optimize object, which is basically a solver for optimization problems. Next, we will define our variables. So variables equals c3 dot ints, which is a function that constructs a bunch of integer variables. So this is how we'll subject ourselves to the integer constraints. So we need a number of variables equal to the number of buttons. So for I in range length buttons, we'll have a name for a variable that is going to be, we'll just call it n sub I. So our variables will be this. And then we'll add the constraint that each variable must be greater than or equal to 0. So o.add, I guess for var in vars, o.add var greater than or equal to 0. So this notation just simply works because in Python you can overload operators. So Z3 has overloaded the double underscore GE function, which basically allows you to implement custom functionality when using the greater than or equal to operator. So rather than returning a true or false value for whether or not the variable is greater than or equal to 0, this actually returns an equation object that denotes variable greater than or equal to 0. And then we'll add the constraints for the joltages. So for each joltage, so for I joltage in enumerate joltages, I is the position of the joltage indicator, and joltage is the actual value that we have to reach. So we should end up with this basically. So I is this subscript number here, and joltage is this value here. So to this equation, we'll want to obtain this sum of variables, which is just going to be all of the variables, all of the buttons that contain this joltage slot. So for B button in enumerate buttons, also we'll set an equation object initially equal to 0. For B button in enumerate buttons, this button affects the joltage if I is in the set of affected joltages. So if I in button, then equation plus equals variable B. So what we're doing here is we're taking the sum of all variables that correspond to buttons that affect that joltage. And so now equation is the left-hand side that indicates the resulting joltage when we press each of these buttons the specified number of times. And so equation must equal joltage, basically. So we'll add that to the constraints as well. And so looking at the first example, we have this as our optimized object. We've declared 6 integer variables. We're asserting that all of them are greater than or equal to 0. And now we're asserting also that n4 plus n5 equals 3. Which makes sense because the 3 is the number 3 is the joltage that we must have in slot 0, and n4 plus n5 are the buttons that have 0 in them. We're asserting that n1 plus n5 is equal to 5, which makes sense, and etc. And then finally, we will call o.check to check the validity, I guess. I don't actually know why this step is required, but if you don't do it, it doesn't work. Again, I am not very experienced with this library. And then finally, we'll do o.model to obtain the answer. So you'll see that this now gives us an answer, which is the resulting value of all of the variables. And we'll note that this is not optimal, and that is because I forgot to actually tell it to optimize anything in particular. Finally, we'll need to optimize. So the thing that we're trying to optimize is to minimize the sum of the variables. And so now, did that work? Yes, that did work. Okay, so now we see that we get our optimized answer, where the first machine requires a minimum of 10 button presses, which was once on the first one, thrice on the second. Okay, we have a different solution than the problem statement specifies, but it still works because the total number of button presses is still 10. So it works just fine. finally, we need to actually extract the data. So O.model gives us basically a context which contains the solution to our integer problem or integer program. And then we can use .eval on the model to evaluate the sum of the variables. And then finally, this isn't a number, it's an int numref. So in order to do stuff with it, we'll also need to call .aslong to convert it into an actual number. And finally, we'll add this to the total. And so honestly spent most of the time on this solution digging through how to actually do this part, because O.model is a model ref, and then you need to figure out how to actually extract the data out of it, and then spend a bit of time not realizing that this wasn't a number. And then I had to find how to get the actual underlying Python number out of the int numref. But in any case, after all that trouble, we do finally get our answer for part 2. So let me briefly recap this problem. Buttons is a set of coefficients which tells us what happens to the joltages when we press certain buttons. So this defines the left side of each equation. Joltages is a vector that we are attempting to target. So basically this defines the matrix and this defines the solution vector, and we are tasked with finding this is the target vector, and we are tasked with finding the solution vector that solves this problem and has minimal sum. This is an integer programming problem, and I unfortunately don't remember how to solve these without using libraries, and I imagine it would also be somewhat unreasonable, as I think it is rather complex. So instead what we do is we just use Z3. We create an optimizer, create a bunch of integer variables because we have to press the buttons an integer number of times, add constraints for each one to be non-negative, find the equation for each joltage corresponding to which buttons affect it, add a constraint that that equation must equal the joltage, tell the optimizer to minimize the sum of the variables, and finally run a check and evaluate it with the optimizer. So yeah, that's how I chose to solve part 2 for today. Please do let me know if this is a special case and if you are aware of a reasonably non-complicated solution that doesn't involve just calling a library, as I do find this rather unsatisfying, but unfortunately I wasn't quite able to figure out something else. So that's all for today's video. Thank you for watching, and I'll see you tomorrow for day 11.